good afternoon to all. Okay, I am Indhumathi from PSN College of Engineering and Technology. I am assistant professor in EEE. Okay, now I am going to take the topic of DC generators. So this is my address, and in that DC generator, we have to see DC generator construction details and principle of operation and commutator process and types of DC generator also, and also characteristics, and then last EMF equation. So first of all, the basic principle of DC generator is it converts mechanical energy into electric energy. We are all known because the generator is input is mechanical energy. For example, in any rotation path, that means oil or any extra circuit, that means mechanical energy, and the output is electrical energy. So in case DC motor, the DC generator output is electric energy. That is the input of the motor. Okay. So first, but now we have see only DC generator. Okay. Okay. So first, the construction details of DC machines. So DC generator or DC motor, the common of the construction. Okay. So first the yoke and the rotor, stator, field electromagnet, pole core and pole shoe, brushes, shaft, armature, coil, commutator, and last bearings. So in the construction details, please take imagine we have to cut the DC generator in center part. Okay, so in that case we have seen this shape. Okay, so in this shape the top is eye bolt. So this is a one screw bolt, and the second field coil. So in the field coil is wounded on the field pole core, and after the pole core the pole shoe is placed. So the pole shoe is because of the flux is spread everyone. That means the pole shoe is placed, and then armature core. So the armature core is rotating path. Okay, then armature conductor is a armature winding the same. So the armature winding is placed in the armature conductor core slot. Then brush. So the brush is placed last of the DC machine to collect the current purpose, and the commutator also to reversal of the current. That means positive negative. Okay, then shaft. The center part is shaft. In that shaft we take the current. And this is also the main part of the 4-pole DC machine. Okay, so the 4-pole means north south and also north south. Okay, so in that north pole, the pole core is the field winding is placed on the pole core, and that this is pole shoe. So the pole shoe is nothing but it is spread the flux to every part. Okay, and the commutator. So the commutator is to reverse the current, positive to negative. That means for switching operation. And the frame is for only mechanical support. So in the detail below we have to see. So this is a practical DC machine. So the outer part is a yoke. This is a mechanical support of the machine. And next the yoke, the stator is placed. The stator in field winding are placed. The field coil and field winding, and next to the field coil the armature winding is placed, and next to commutator, and next to brush and shaft. This is a practical DC machine. Next, the first part is yoke. So in this large machine, in this case, the yoke is very big part, and the smaller machine, small DC machine, the yoke is in this like this. So first, it acts as a frame of the machine, and it gives good mechanical support, and it is used for low reluctance for magnetic flux, because we need more magnetic flux. That's why the frame is used. So high permeability for small machines, the cast iron or low cost, and for large machine cast steel. So small machine cast iron, and the large machine cast steel is used for manufacturing for high permeability. And pole core and pole shoe. So pole core means we have to wound the field winding in that pole core. Okay. So in the field magnet, the pole core is a pole body. So carry the field coil, and it is like rectangular cross sections, and laminate. It must be laminated because reduce the heat loss. Okay, it is fit on the yoke of the machine. Okay, through bolt. That means the first we have eye bolt and pole shoe. So pole shoe act as a support to field pole and spread out the flux. Okay, so the main thing spread out the flux, that is the main thing, and this thickness is 1 millimeter to 0.25 millimeter. Okay, next, pole core and pole shoe, the continuous of the previous slide. Okay, so the field magnet, the field coil is placed in the pole core. So the diagram clearly show the field core. In that field core, the field coil is wounded. So in this exciting coil or magnetizing coil, it provides the excitation to the rotor. So the number of poles depends speed of the armature and the output for which machine design. So frame is used for designing exciting coil. So different type of excitation, separately exciting and self-exciting. So in the separately exciting, so this is a place give the motors separately. In the self-exciting, the residual flux, that means initial flux is already placed in the rotor. That flux is, that current is used to do recycle process. Okay, then armature core. So the armature core, like this say, this is the armature core, and this is a keyway for brush or for shaft or commutator is placed, and this is a air hole. Okay, so reduce the heat, and this is a slot to wound the coil, and this is a teeth. So it is depend upon the speed. Suppose we have more speed, the slots are very reduced. In that, these slots are very large number of slots, so the speed is low. Okay, so this is a lamination path, and this is a keyway, and this is many armature plates. It is a one armature plate. So difference between the many armature plates are attached. This is one armature plate. Okay, then conductor system. So then the conductor system, the armature core, the field armature coil is wound on the armature core. This is a conductor system. Okay, to support the armature winding and to rotate the conductor in the magnetic field. So it is cylindrical or drum shaped is built. Okay, it is made up of high permeability silicon steel. So because the silicon steel is a high to pass the current, this is a good conductor, and the semiconductor also. Each stamping is separated from its neighboring one by thin varnish insulation. So laminated to reduce the eddy current losses. So the main loss is eddy current loss and hysteresis loss. So to reduce the eddy current loss, we have to laminate the surface of the and windings. Okay. So there is a two losses, hysteresis and eddy current loss. So in these two losses, we have discussed later. So the ventilating ducts are providing to dissipate heat generated by above losses, because the losses are in the form of heat. So we have to reduce the heat means we have must ventilated duct. Okay. So then armature winding. So the armature winding is same as that of the armature conductor. Armature conductor is an armature conductor. Copper coil is used, or copper or aluminum. So for the small machine, we have used copper. For the large machine, we have to use aluminum. Winding are insulated each other. The commutator. So the main segment is commutator, because the commutator have many segment. Okay. So in this segment is for main purpose is to convert the current positive to negative, and between the positive negative it have zero. So the main purpose is switching operation is placed in that commutator. Okay. So between armature and external circuit, split ring AC to DC. This is the armature diagram, commutator diagram. This is a practical diagram. This is a bearings and bearing and brushes. At last the machine, the brushes are placed to collect the current, the main process. So in that brushes, carbon or the carbon graphite are used, because they have low resistance path and they have very high power losses occur in that brushes. So shaft and bearings. Shaft, the mechanical link between the prime mover and armature for free rotation. So bearings are used. In that shaft, the mechanical link. So this is a DC machine stator part. Okay. So the winding are field winding are placed in pole core, and pole shoe is we have the poles. These poles, two poles are pole shoe. Okay. This is a stator part, and the outside is yoke, motor house yoke, and this is a leg. Then this is the inner part. This is a rotor. So not a rotor. This is rotor, and this also commutator and shaft, and also in bearings. So bearings for free rotations. So the coil commutator interconnectors. So in that coils we have two types, a lap winding and wave winding. So we have discussed later. And this is our for lost the brush. So the brush is placed in that frame. Okay, the brush is used to correct the current, and this is a copper graphite brushes. The graphite is a very important things in that brushes, and this is spring for free movement and the commutator segment. Okay, these are finished construction parts, and next we have to see working principle of the operations. Okay, so first of all, the basic principle is to convert mechanical energy to electric energy. So when a conductor move in a magnetic field in such a way, conductor cut across the magnetic flux line. So whenever they cut the magnetic flux, the EMF is produced in a generator. This is a generator according to Faraday's law of electromagnetic induction principle. Okay. Next, the first law. So the electromagnetic induction principle is very important principle. So the first law is said whenever the magnetic flux linking with a circuit changes, an EMF is always induced in it. Okay, or whenever a conductor cut the magnetic flux, an EMF is induced in that conductor. So whenever the conductor is cut the magnetic flux path, that the EMF is induced at that part at the second. So second law, the magnitude of the induced EMF is equal to rate of change of flux linkage. Okay. Next, this is the graphical diagram of the DC generator, simple generator. So in that generator said, and we have north pole and south pole. This is a field winding, that means stator, and this is an armature, this is a rotor, and this is shaft and brush. So the brush is going to output, that means EMF equations. Okay. So Faraday's law of electromagnetic induction. So this is a graphical image. The changing of magnetic flux through a loop of wire induces the electromotive force. Okay, so the magnetic flux are created in that magnet, and it is going to an electrical copper. So whenever the cut the magnetic flux in the conductor, the current is induced. The induced current is maybe positive or negative for the flux, depend upon the flux. Okay. Lenz law. So Lenz law nothing but it induced the conductor or in such a like the direction oppose the change of magnetic field. So it is only change the opposite direction to produced current. Fleming's right hand rule. Okay. So Fleming right hand rules, the three fingers shown that the generator principle. So the thumb finger represent the direction of the motion of the conductor. Okay. So then the first finger, forefinger represent field, and the second finger, middle finger represent current. Okay, current. Then Fleming right hand rule. So the direction of the motion means the conductor, that means the rotor rotation, the conductor direction. Okay, the direction of flux, normally the flux is going from north pole to south pole. Okay, so direction of EMF, the induced EMF is the conductor output side. That's a Fleming right hand rule. So the Fleming right hand rule is used only in generator. In motor, Fleming left hand rule is used. Okay. Then the followings are basic requirement to be satisfied for generation of EMF. These are main three things. Okay, the three things are the uniform magnetic field, a system of conductor, and relative motion between the magnetic field and conductor. These are three things. The absence of one thing, it will not happen. So the magnetic field, that means permanent magnet or electromagnet, practical things. In this two, we use anything. The conductor. So the conductor means copper or aluminum. And relative motion means prime mover, turbine, and IC engine. These things are very important. And this simple loop generator, we already discussed. And the basic generator also. So this is a pole piece, that means field. And the flux is passing from north to south. Okay, the magnetic field and armature. These are load and brushes to collect the current, and slip ring is to reduce the loss. So this is a basic generator we already discussed. So whenever the conductor cut the magnetic flux, the EMF is induced in the brush is collect the current. So first the armature rotate from 0 to 90 degree. Okay, so the conductor cut through more and more line of flux, building up to maximum induced voltage in positive direction. So in 0 to 90 degree, beginning it goes in that first of all it in position is 0 degree. So in that 0 degree the magnetic flux and the armature conductors are parallel, so there is no touch and no cut. This means that no EMF is induced in that, so the plane graph is shown. But after the 0 to 90 degree, it perpendicular to the magnetic flux, that's why we produce the current in 90 degree, and then 90 to 180 degree. So 190 to 180 degree in continuous less lines of flux, because it going to another direction, so decreasing the voltage. Okay, next 180 to 270 degree. 180 to 270 degree, the conductor cut more and more line of flux, but in the opposite direction, so voltage is induced in negative. Okay, so next 270 to 360. So 270 degree, the same meaning, but decreasing from maximum negative level to 0. So the EMF is generated in one revolution, one rotation, the one cycle is happened. So this means this is faster and faster, and the EMF is induced in very fast. And this is armature winding, because the armature winding is the main part to produce the current. In that armature winding have two types, lap winding and wave winding. Okay, so this is a armature winding. So this shape is very critical. Please see that figure. So this is a north pole and south pole. The north pole is a red indication mark, because this is a magnetic flux producing path and is going to north pole to south. And the armature conductor. So armature core is not there. Armature conductor is here. So stator field and commutator. Okay, and brushes are there. So this is a graphite brush to collect the current to load. Okay, so then lap winding. So the lap winding means used in machine designed for low voltage and high current. So this is used only in low voltage and high current machines only. Armatures are constructed with a large wire because of high current. Example, it is used in the starter of motor, almost all automobiles. So the lap winding is all are used in all automobiles. The winding of lap wound armatures are connected in parallel. This permits the current capacity of each winding to be added and provide a high operating current. So in that winding, we have to solve some problems. So in that problem, the area is equal to, that means parallel path is equal to number of pole, because the lap winding area is not given in that problem. So the poles we have so the poles is equal to area of path in lap winding only. And then wave winding. So in that wave winding, it is used in design high voltage and low current, but in the lap winding low voltage and high current. Okay, so their winding are connected in series only, but in that parallel. So that's why we have the number of parallel paths, means A is 2. It's a constant. Okay, this is also using small generator. So the wave winding is used in small generator only. And this is the lap winding. So lap winding is series parallel connection. All things are different windings. All windings are each and each very different. But in wave winding, one input and another are current series, and the output is compared to same input. This is a wave winding. Clearly understand? This is the commutator part. Okay, and this is a lap winding. So the lap winding or parallel connection, lap winding or parallel connection. So all are separately connected. And wave winding, wave winding is series connections. So and each and every one is connected in series to connected in one to another. Okay, so this is a wave winding. And next, commutation process. So in the commutation process is a position of the DC generated brushes, so that the commutation segment changes the brush at the same time armature current change direction. So the armature segment on the brushes changes are happened. So from that brushes changes, the armature current direction also changes. Okay, Then this is EMF equations. The computation process are finished, and this is the EMF equation of the generators. Because the EMF is the output of the generator, that's why we have to derive the EMF equation also. So first, flux per pole. The unit is Weber, and Z total number of armature conductor and number of slot. Number of conductor in slot. Okay, Z the number of conductor into number of conductor. And pole, number of generating pole. A, number of parallel path. And N, armature rotation of the revolution per minute. And E, EMF induced in any parallel path. So first of all, generator EMF EG is equal to EMF generated in any one of the parallel path, that is E. Average EMF generated per conductor is equal to d phi by dt. Okay, there is a basic formula. This is a Lenz's law formula also, d phi by dt. So now flux cut conductor in one revolution. So d phi is equal to phi p. So number of revolution n by 60. So dt is equal to 60 by n. That's why d phi in the d phi 5p and dt is 60 by n. So the n is a lower side of the decimal. That's why we have to put in that upper part. That means numerator. Number of conductors equal to Z by E. So EMF generator is 5 Zn 60 Z by E. Then generated EMF EG. So this is the formula. We have to separate the 5 Zn divided by 60 and P by E. So the wave winding A is 2 and light winding is equal to P. This is the main thing. Okay. Okay. So then we have to discuss about types of generators. So DC generators and AC generator. In the now we have only see about DC generator only. So from the DC generator, the types of self-excited, separately excited. So and below the separately, there is no happened. This is an ending. And the self-excited we have to shunt, series, and compound. In that compound, long shunt, short shunt. So long shunt, short shunt, cumulative differential. Cumulative differential. Okay. So next, types of generators. So separately excited, and we have to see in the previous slide. So classification of generator. The separately excited means the field winding supply is given separately to the armature winding. But in the self-excited, the field winding are seriously connected, shuntly connected, and compoundly connected in that closed circuit. But in separately excited, the circuit is differently separated. Next, separately excited. So this is a separately field winding. The field winding is given to different supply and separate supply, and the field winding produce some energy. That energy is given to the generator. So I is equal to IN, and E is equal to VT plus IA RE, and BC is a back EMF. And shunt wound. So shunt wound. The shunt field winding is given to the parallel to the generator. So the formula is IL is equal to IA minus IS sketch. Okay. So I is equal to IL plus IS sketch. So now generating EMF formula is VL plus IARE plus BCD, brush center drop. Okay. And series generator. So this is all self-excited motor. So self-excited generator, shunt wound, and series wound. The winding are seriously connected. So the formula is different. IL is equal to I is equal to ISC. So the EG is equal to VL plus IARA plus ISC RC. And then compound wound rotor. So in that generator, long shunt and short shunt. In that long shunt and short shunt, what is the difference between that long shunt and short shunt means? This is a current are different, and this current path is different. So in that path, all currents are different side. But in that fault, the armature current IA is equal to load current. This is the and the load current series current IL is equal to IL. So this is same the current direction. The difference between the long shunt and short shunt. Then the practical DC machine, DC generator characteristics. So this is a very simple characteristics, open circuit characteristics, and internal characteristics, and external characteristics. So open circuit characteristics means there is output side, there is no current and no load. That means the open circuit characteristics. So suppose the inputs are connected perfectly, and the output side only the circuits are open. That means the wire are not connected to load. That means example bulb or fan. That is the open circuit. We have only measuring purpose. Then internal characteristics. So internal characteristics means armature in the center of the machine armature. The armature, what happened? That is the internal characteristics. And external characteristics means load characteristics. So the load is given, and that what is changes in that current. That's the internal characteristic. And the critical field resistance. Okay, what is the meaning of critical field is term associated with the DC shunt generator. The value of resistance of shunt field winding beyond which the self generator failed to build up its voltage is known as critical resistance. Okay, and as a given speed as a maximum field. So in that separately excited there is no condition, but in the self excited some conditions are given. That means critical field resistance and critical speed. So beyond the critical resistance and critical field resistance, the self generator is off condition. That is the critical field and critical speed. This is an open circuit. So in that open circuit, the EMF is increased and field current also increased. There is no change in linear increase. There is no decreasing part because the load is not connected. And there is a critical resistance, critical speed, and condition of voltage build-up of the shunt generator because there must be some residual magnetism in the generator pole. This is the first condition. And the connection of the field winding should be such field current strengthens the residual magnetism. So resistance of the field circuit should be less than the critical resistance. In the other word, the speed of the generator should be higher than the critical speed. So these are a happen. The condition of voltage build-up of shunt generator is possible. Next, open circuit characteristics. So this means separately exited generator, open circuit, there is a no load connected between the output. There is a open circuit graph. And internal external characteristics. The voltage drop across the internal external characteristics, but there is no load. That means there is a straight path. And characteristic of shunt generator. This is self-excited shunt generator. Open characteristics and the internal characteristics and external characteristics. So in that open characteristics, the voltage and current is linearly increased. And the external characteristics, the voltage is increasing and gradually, and the current is constantly increasing. And then internal characteristics, the armature reaction drop is across in that voltage drop. And then characteristics of the series generator. So the same as that of the previous shunt generator. And the compound generator, shunt, long shunt and short shunt. So in that the voltage is flat compound. Suppose the voltage is increasing. That means it's a over compounded. The voltage is maybe decreased. That means under compounded. So applications in the separately excited generator, these are used for speed control of DC motor over a long range. These are used in area where wide range of terminal voltage is required. And self-excited generator. So self-excited in that self-excited shunt generator. These are used in excited synchronized machine and separately excited AC generator. Use a battery charging purpose and the ordinary lighting purpose and power supply purpose we have to use shunt generator. Series generator, arc lighting. So in that arc lighting we use series generator and series incandescent lighting. Okay. Then constant current for welding purpose. This is the series generator is used. And compound generator. So in that compound generator, cumulatively compound generator and differentially compound generator. So in the cumulative compound generator, heavy power service in the railway station. That means we use a compound generator. So the differential compound generator is type of very rare. Special application like arc welding. Only we use arc welding. This is a rare purpose. Armature winding we see already. And this is a practical armature winding. So the armature winding is placed in the rotor path. This is a rotor path. And this is a brush holder. Okay. Next, losses. So losses is copper loss, iron loss, mechanical loss. There are 3 losses in that all machines. So the copper losses means armature copper loss, shunt copper loss, and series copper loss. And iron loss means hysteresis loss, eddy current loss, and mechanical friction loss, windage loss. And another one loss is strain loss. So we have discussed about later. And copper loss. So the copper loss is armature copper loss, field copper loss. In that field copper loss, shunt copper loss, and series copper loss. So in that armature copper loss, the armature resistance are losses due to brush contact. Okay, this happen due to brush contact. and the shunt field winding. The field winding also same. And iron loss, hysteresis loss and eddy current loss. So hysteresis loss is mainly due to a reversal of magnetism because the north pole and south pole directions alternatively changing alternatively. That's why the reversal of magnetism, the hysteresis loss occur. So to reduce the hysteresis loss means we have to laminate the surface. Then eddy current loss. So eddy current loss is nothing but it's in initially we produce EMF. In that case, the EMF is produced so many of current. Initial current is very high. So that current is in the form of heat. So the winding got damaged or spark. So that's why eddy current losses occur. To reduce the eddy current loss, we may simply do lamination. And mechanical losses. So mechanical losses means friction losses and windage losses. So friction loss, windage loss. Friction loss due to bearings and windage loss due to air gap between the armature and pole shoe. So in that loss we have to reduce by the closed path of the pole shoe and the armature core. So the stray loss. The stray loss is combination of magnetic losses and mechanical losses. So the power stages. So power stages from first beginning mechanical power begin to the iron and friction losses and electrical power generation, that's the copper losses and electrical power output. So mechanical input and power developed and power output and mechanical efficiency. So total watts generated in armature to mechanical power supplied and electrical efficiency watts available in a load circuit and load watts generated. Overall commercial efficiency watts available in load circuit mechanical power supply. Then efficiency of DC generator. So the basic formula is output by input into 100. So from that output, the input minus losses. So the output is discussed and the input is output plus losses. No input is given. So the efficiency is calculated by output by input into 100. And this is the efficiency. The maximum condition of maximum efficiency means variable loss is equal to constant loss. This is the maximum condition. So these are all the topics of the DC generator. Thank you.